Okay, we're good to go, Janet. Start whenever you're ready.
All right. Hello, everyone. My name is Janet Pauli. I'm a director on the Potter Valley Irrigation District Board. On November 14th, there was a town hall meeting for the community of Potter Valley to update people on a study that's being done to look for surface and groundwater options for water storage. Before we learn about Jacob's work, who's the company that's doing these studies, let me give a brief history and background for why we're here this evening. For over 100 years, water has been imported to Potter Valley by Pacific Gas and Electric via the Potter Valley Project, or PVP. That Eel River water has been available year-round due to storage of winter water behind Scott Dam on the Eel River. But PG&E is decommissioning the project. This will result in removal of Scott Dam and also Cape Horn Dam, which is needed for the diversion. From 2019 to 2022, IWPC and other Russian River interests explored acquiring the Potter Valley project to keep the dams in, but we could not make it work because of timing and funding issues. Now Mendocino County Inland Water and Power Commission and Sonoma are negotiating with PG&E, tribes, and other stakeholders to build a new diversion, the new Eel River facility, or NERF, as we're calling it, and acquire the right to divert this water into the future. I'm going to turn this over to Tom Johnson for a few minutes, who is the consulting engineer for the Mendocino County Inland Water and Power Commission. And the Power Commission is a joint powers authority representing the cities of Ukiah, Potter Valley, Redwood Valley, the County of Mendocino Water Agency, and the Russian River Flood Control and Water Conservation Improvement District. Tom is going to describe the current PG&E timeline for the decommissioning, and he'll also describe what the NERF facility, the initial engineering of the NERF facility looks like. So Tom, could you take over here?
Thank you, Janet. My name is Tom Johnson. I've been working in water and power in California for just shy of 40 years. As Janet mentioned, the current Potter Valley project is being surrendered. The FERC license is being surrendered by PG&E. It's been an interesting and complicated process up till now with many twists and turns. The current pathway is fairly stable, though. PG&E intends to file its formal surrender application by the end of July of 2025. That will kick off a very extensive and somewhat uncertain regulatory process. FERC is the lead in this process, and it will review the application and perform NEPA analysis. In parallel with that, a number of state agencies and at least one other federal agency will also review the application and ask questions. Once a surrender order is issued, then PG&E will move forward with design and implementation of dam removal of both Scott and Cape Horn Dam. As I mentioned, this is a highly uncertain process. The best guess is that we wouldn't see dam removal before 2030. It is entirely possible that that timeline would be pushed out further. These are complicated proceedings. As I mentioned, a number of different state and federal regulators will need to opine on the proceeding, and it sometimes takes a little bit longer. When we do wind up with the dams removed, the Cape Horn Dam and Van Arsdale Reservoir will be replaced with a new pumping facility. The next two slides show the current, if you could advance, please. Can we advance? Thank you. This is a rendering of the existing Cape Horn Dam and Van Arsdale Reservoir as it exists today. The dam spans the river. There's a fairly large abutment on River Right, and the intake for the tunnel and then water delivery over to The Russian River side is further upstream of Cape Horn Dam. The next slide shows a downstream view of these facilities with Cape Horn Dam spanning the river, the abutment on river left, and various fish passage facilities, including fish barrier, fish ladder, and a couple of structures for counting stations on river left. The next slide shows the proposed facility to be constructed in its place. So you can see here that Cape Horn Dam has been removed right down to mostly bedrock and perhaps a small residual footing. That would be the new threshold for pumping station. There is a pump house located what would have been immediately upstream and on river left of where Cape Horn Dam was. The embankment on river right has been cut down substantially, and there's a new retaining wall and backfilled area on river left between the pump station and the tunnel inlet. There's a large diameter pipe that goes from the pump station to the tunnel inlet. In the future, water will be pumped and lifted from the river. It's a fairly short lift. It's only about 25 feet, and into the tunnel and then through the mountain and released down the other side in substantially the same configuration. The final slide shows another view of the new facilities from further downstream. You can see that under low and modest flow conditions, this would be sort of a modest flow condition, a couple thousand CFS. We would expect essentially unimpeded river. All of the any remaining foundation or bedrock in the vicinity of where the dam was would not be a barrier for fish, so fish could move easily up and down the river. The pump station would have appropriate fish screens and other facilities to make sure that there is no harm to any aquatic resources. The fish ladders and structures and so forth would all be either abandoned or removed, depending on PG&E's design for those facilities. That's an overview of what's to come, both in terms of schedule and future facilities. The next phase of facility pump station design is underway and will be updated in the next 18 months or so. Janet, back to you.
Thanks, Tom. So continuing with the discussion of why we put on this town hall meeting earlier this month, without the dams on the Eel River, the newly diverted water is going to be available for diversion only in the winter and spring. Potter Valley will no longer have benefit of nearly year-round water flowing in the upper Russian for Potter Valley Irrigation District to divert, because Scott Dam, holding that current supply of water that is stored from winter rain and snowmelt, will be removed. This little graph just shows what we all know, that rainfall normally tends to end in April and May every year, after which we will be dependent upon providing more storage than here in the valley, rather than having Scott Dam to rely on. And the next slide. So some of the water diverted in the wintertime can be stored in Lake Mendocino, but Lake Mendocino storage is limited due to the way in which the lake is operated by the Army Corps of Engineers. But even water that can be stored in Lake Mendocino when storage space is available will not be easily available to Potter Valley. And that's because of the high cost of pumping it back uphill to Potter Valley and water rights issues that would likely make it prohibitive. Instead, we need to explore how to store winter and spring Eel River water in Potter Valley to maximize use during the summer irrigation season. And that's why Jacobs has been working with us to try and look at options for that kind of storage. The flows that will be coming through the project have been estimated based on the work of McBain and Associates. And this table is very detailed. It describes how fall, winter, spring, and summer flows will be calculated based on different species of fish and their life cycles, and on the natural flows in the Eel River. And we, as a group of partners, will be presenting these diversion rates to federal and state resource agencies for approval. And the next slide. So based on these diversion rates, we need to evaluate the best locations to store water. We need to consider the cost, efficiency, size, and a host of other factors. We also need to explore other potential sources of water for Potter Valley, such as local groundwater and tributary flow, which can supplement Eel River water. All of the options could help Potter Valley by supplementing or storing the Eel River supply. And these options may also help downstream users in addition to Lake Mendocino storage capacity. But we need to recognize that there will be a new and large financial commitment to pay for this, so we can still have summer irrigation water. Before I turn this over to Jacobs for a discussion of their work, I'd like to have Stephen Maples with Sonoma Water take a few minutes to talk about Sonoma's role in the Potter Valley Water Supply Reliability Study. There you go, Stephen.
Thank you, Janet. Good morning. My name is Stephen Maples. I'm an engineer at Sonoma Water in the Water Resources Planning Group. And you may be wondering why Sonoma Water is involved in this study in Mendocino County. And the short answer is that Sonoma County and Mendocino County, both areas that rely on the Russian River, are both similarly affected by any future changes to the Potter Valley project in terms of water supply reliability. And really, the longer answer is that there are sort of three aspects of a future diversion facility that all need to come together in order for it to be successful. The first is that we need to identify a consortium of water users in Mendocino and Sonoma County on the Russian River that would be able to help pay for the project and rely and pay for water that would come through the project in the future to pay for continued operations and maintenance. The second aspect is we need to ensure that the Potter Valley project is the actual facilities are able to be modified so that they can be operated under a future without Scott and Cape Horn Dam and continue that diversion well into the future. And then the last aspect is that we need to find a solution so that, like Janet mentioned, water that is available from the Potter Valley project just during the winter and spring can be stored locally within Potter Valley so that it can be used during the summer irrigation season. And so in order to do this, Sonoma Water submitted a grant application to the California Department of Water Resources in November 2021. And at the end of December 2021, Sonoma Water was awarded a $2.1 million grant for this study. And that study included three components to the award that roughly align with what I just mentioned. So there was a Russian River Forum, which was sort of a watershed-wide collaborative effort to help identify those water users who would potentially come to rely on a future project. There was the Potter Valley Project Diversion Assessment, which was recently completed by McMillan and Associates to develop the preliminary design for a new Eel Russian diversion facility. And then the last component of that award was the study that we're talking about today, which is the Potter Valley Water Supply Reliability Study. That work has been done in collaboration with Mendocino County IWPC and Potter Valley Irrigation District to identify the water supply alternatives for Potter Valley. And that work has been undertaken by Jacobs. And today we have two representatives from Jacobs to describe the details of the study and the results of it. We have Armin Munevar and Nate Brown, which will be going through the results of that study here. And with that, I'll pass it off to Armin.
Yeah, thanks, Stephen. And good afternoon, good morning, depending on when you're listening to this. My name is Armin Munevar with Jacobs Engineering, and we're really here today to talk about that last component that Stephen Maples just mentioned, the Potter Valley Water Supply Reliability Study. We'll be going through kind of these elements here on our agenda, a little bit of background of the project, some of the field investigations that were being conducted as part of this effort. This included both geophysical investigations, well monitoring, and exploratory borehole drilling. We'll then talk about some of the numerical groundwater flow modeling that has been conducted, and then shift more of our forward-thinking aspects of the study in terms of the water management alternatives and what we're finding from that analysis. And then we'll wrap up with some next steps. So I think, yeah, if we can go to the next one. Thanks, Nate. So as both Janet and Tom and Stephen mentioned before, right, the Potter Valley project has provided a critical supply for the Potter Valley for over 100 years, and the changes that are underway and foreseen will have a substantial and profound impacts on water supply, agriculture, and the community in the valley. We know that those impacts will be felt within the valley, within Lake Mendocino, and within the Russian River downstream of Lake Mendocino. The focus of this effort, though, is fully within Potter Valley. So really a focus on how could Potter Valley manage and adapt to a changing condition of the Eel River imports. A big focus of this effort has been to create a detailed understanding of the water resources in the valley, to quantify those potential future impacts, and then look for solutions that can achieve sustainability under a changed condition. And as Stephen just mentioned, this effort that we're talking about that Jacobs has conducted has been funded through a grant from the California Department of Water Resources under their 2021 drought funding. Okay, this is a map showing on the right-hand side, showing the overall contributing watershed within the East Fork of the Russian River. Our focus has been predominantly in the Potter Valley region and the Potter Valley groundwater basin. So you can see those are outlined in red is the Potter Valley groundwater basin, and the upper watershed is outside of the red area. Our key objectives have been really to focus on characterizing the water resources, helping to understand different perspectives of impacts, risk, and opportunities, and then evaluating determined water supply strategies. We have some recommendations at the end of this presentation for looking for kind of robust water supply solutions. They are not recommendations of a specific alternative, but recommendations for subsequent analysis and future work. But we do feel we have some interesting findings here today that will guide some future discussions. Next slide. Okay, I think if there's some animation here, we could just let it all flow through, and we've taken a kind of an adaptive approach to the project, really characterizing it in three components. The first part of our project was understanding the water resources and the water balances. So we've reviewed previous studies and available data. We've had a good partnership with Potter Valley Irrigation District, and they've provided lots of the maps and the GIS and the historical water supply data. We've also been working with USGS and building off of some of their previous work. We developed an early conceptual model of the water resources of the valley early on in the project. And then we kind of went into the second phase of the work, which was characterizing the hydrogeology and agricultural practices. We did some field characterization, agricultural assessments. We've collected both remote sense data and field observational data. And then we worked into the third phase of our work, which was to take this conceptual model, expand it into a true numerical model that had better characterization of the valley, and then use that baseline condition and the future without Potter Valley project to look at what water management alternatives could be evaluated and what is the pros and cons of each of those. Next slide. So we broke them into essentially 9 tasks. The ones that are bolded were the ones that were still underway as of November 14th. We're focused on really today talking mostly about, we'll talk about the whole project, but a heavy focus on the task 6, which is the integrated flow model, and task 7, which is the water management alternatives. Next slide. Okay, I always feel like it's useful to start with kind of the basic data and assumptions to make sure kind of have a broad understanding of what the scale and scope of the problem that we're trying to grapple with. We didn't develop everything new as part of this effort. We built quite a bit on previous data sources and estimates. A number of those came from Potter Valley Irrigation District in terms of land status reports and delivery data. We used remote sense data through a product called OpenET to characterize the actual evapotranspiration. Importantly, we built off of a hydrogeologic framework model from the USGS, which had a subsurface characterization. That was our starting point for moving forward. We used from UCSD through the Scripps Institute. There's a stream gauge network that's in the upper portions of the tributaries of the Potter Valley. We use some of that data for validating the model. We used DWR well logs. We had geophysics that was implemented as part of this effort. And then we've built off of existing estimates of what a run-of-the-river diversion might look like. So there were lots of prior data sources we used, and then the studies that were most recent, the Macmillan report that Stephen mentioned, that was looking at the diversion, but a previous report in 2021 also looked at water supply alternatives in the Potter Valley. We built off of that, as well as previous work looking at surface and groundwater investigations throughout the valley. Go to the next slide. So we built off a lot of that previous work, and I think this slide here hopefully frames that up quite well. And so this is looking at, this slide is showing from 2010 through 2022, kind of the recent period. These are water years. And the first bar that pops up here, the gray bar, is looking at Potter Valley Irrigation District diversions from the Potter Valley project. And you can see here it's been roughly 14,000 acre feet of diversion in the early part of the 2010s to maybe 2018 or so. You can see there's been changes in that diversion. It's been reducing in the more recent period, and then during the drought period has seen some low estimates. The next bar that pops up, the blue bar, is showing how much deliveries from Potter Valley Irrigation District to customers, to the contractors within the valley. And you can see that's been somewhere on the order of maybe 8 to 10,000 acre feet in the most recent period, although it's been up at 10 to 13,000 acre feet in the middle of the 2014-15 time horizon. And that's these are all annual numbers right now. And then the next bar that pops up here is the light blue bar. And this is looking at kind of the summer irrigation season. And so now we're trying to focus, I think Janet did a nice job of showing that rainfall plot, and basically by April, May, the rainfall stops. And so really this period of deliveries that were previously provided during June through September represents kind of the bounds of what we're trying to potentially mitigate for because of the loss of the imported supply. And we're looking at somewhere on the order of 8,000 acre feet. So if you look at the most recent periods, the 21 and 22 are drought periods, so somewhat anomalous. But if you look at 2019 and 2020, you see we're roughly at around 8,000 acre feet during that summer period. And then we wanted just to do one more validation. So we have the green bar that pops up here is an estimate of the actual evapotranspiration from crops within the valley using the OpenET remote sense data. And you can see we're somewhere around maybe 5,000 or 6,000 acre feet of total evapotranspiration. This is the amount that the crop and the plants actually evapotranspirated. So kind of putting this into perspective, this is the amount and the volume of water we're looking at, both an annual and a seasonal aspect that potentially needs to be mitigated through alternative management of water resources in the valley. Okay. So I'll switch first to the field investigations. So we'll talk about the geophysics, well monitoring, and new monitoring wells. We can go to the next slide. And so the geophysical investigation, so there were kind of three elements to that investigation. The first was a review of USGS work that had previously been done using a gravity survey method, looking at the subsurface, and essentially we're trying to peer into the subsurface to understand if there are major areas of gravel or sands or clays that might influence how we think about the groundwater system. We had initiated the effort with a drone-based electromagnetic survey, and those are shown in the orange lines on the map to the right. Those were areas where the drone was flown with equipment that hangs from that characterizes the subsurface by bouncing electromagnetic waves to the subsurface. We were only partially successful in getting a few transects completed with that drone work at the time. We then augmented with a pretty substantial electrical resistivity transect surveys, and those are all shown in the blue lines on the map to the right. And these are all the sections in which we conducted ground-based electrical resistivity surveys. And all of this work, and so each one of those lines and the numbered blue lines there are the transects. And the figure to the left is a result of one of those transects. The top figure is the electrical resistivity. That's how it's actually measured in resistivity. So we get these colors of highly resistive and low resistivity areas. And then there's a translation of that, an interpretation that high resistivity equals certain types of subsurface conditions. And so the bottom graphic is an interpretation of that resistivity into sands, gravels, and consolidated rock in the yellows, and clays in the brown areas. And that's what the bottom graphic is displaying. And so we have, I think the next slide then shows a more detail of that. So we can go ahead and, this is a kind of an angled view of the valley. Each one of these transects are shown here. Thank you, Nate. Each one of the transects are shown there kind of at this angled view, and we're looking at the subsurface. And again, the yellows were interpreted to be potentially sands and gravels, and consolidated rock, and the maroon are interpreted to be clay and likely less water-bearing units. You can see each of the DWR wells are also located in this map here. They're very small, but we looked at each of those logs and tried to use that information also to validate the interpretation or help support the interpretation of the subsurface. Okay. So those were the geophysics aspects where we're trying to understand the subsurface by methods that are not actually drilling into the subsurface. We also were looking at monitoring wells. So we have a few holes in the ground in in the valley. First, we focused on existing wells. There are a number of existing domestic wells in the valley. We were able to equip 8 of those existing wells through agreements with the well owners with water level instrumentation. So that is, we're currently monitoring the water levels in those wells to understand whether dry conditions, how much we see a response, and also to see kind of both the seasonal trends and then the response between upper portions of the aquifer and lower. We've also recently completed, as of late November, we completed 5 new boreholes, exploratory boreholes within the valley at sections that we felt that might be higher performing water bearing units or higher capability of storing water. We drilled and sampled those 5 new boreholes. We constructed 3 of those. 3 of those 5 were constructed as new monitoring wells. They are near Bush Creek and then in the middle of the, mostly in the Middle Valley near the East Fork Russian River. From that information, we've been able to look at cores and the lithology, kind of what are the soils at various depths. Those all have been logged. And then we've done some preliminary well development to look at the pumping, short-term pumping on the order of 3 to 4 hours of pumping to determine how much response we might see in the well and how productive might it be. These are small wells. They're 4-inch wells, and they're not designed to be full production wells. So we're getting some data on the subsurface, but it's limited to kind of the size of those wells and not to be interpreted as full production wells. Okay. All right, Nate, I think I will hand off to you for the groundwater modeling.
Great, thank you. Yeah, my name is Nate Brown. I'm with Jacobs Engineering, and I led the modeling aspects of this project. And so moving forward, first off, I'm going to assume that most folks don't really know what an integrated flow model, what that means. So we basically start with the groundwater flow process here. We subdivide a study area into groups of 3-dimensional boxes that we call cells, and they're organized by, rows, columns, and layers. Sort of think of it like a Rubik's Cube, except we have more flexibility in the number of rows, columns, and layers, and our cells don't all have to be the same size. But the idea is you assign parameter values like, say, permeability or rainfall at every one of these cells. And then ultimately the model will compute a groundwater pressure and a groundwater flux to and from its neighboring cells. And that happens through time. So at each output time, there's a lot of calculations being done to achieve that. And then that's basically how that works. So what do we mean by integrated flow model? With this type of model, what we can also do is bring in things like stream segments that may represent streams or canals. And at those locations, we also assign parameter values. How rough is the channel? How permeable is the channel? What is the slope? That type of thing. And these segments are linked with the groundwater cells beneath them to compute that surface water groundwater interaction. Then we take it a step further, and we can integrate things like land cover and land use. So these little polygons I'm showing, they may represent areas of, say, riparian veg or different types of crops. And there too, we would assign parameter values to those that are representative of those kind of polygon areas. And then they are linked or can be linked with both the stream segments for things like diversions, deliveries, and then also linked with the groundwater cell beneath them. So there's a whole lot of calculations being done through time with these things, but think of it basically as just a sophisticated calculator to compute water levels and fluxes throughout a study area. And so why do we need one for this project? First off, the aquifer beneath Potter Valley just hasn't been as extensively studied as a lot of aquifers throughout California, primarily because you've had such a good access to surface water supplies. There just hasn't been a strong need to study it. So that said, there's uncertainty in the subsurface distribution of materials, gravels, sands, silts, clays. And so this type of modeling provides some good benefits, a means to evaluate parameters and processes that are too difficult or impossible to measure in the field. It's, as an example, it's easier to measure or observe flow processes at the surface, but it's not so easy with the subsurface. You have to invest in wells and to get access to be able to look at some things. It helps us more objectively test ideas about how we think the system works. Basically, these tools are built to solve a math problem based on well-established physics-based equations rather than relying on gut feelings. And so that provides some good objectivity for how the system may work. Can be used to help forecast potential responses of aquifers and streams to proposed alternatives. That's how we've used it for this project, and we'll be going over some of that in a few slides. And one of the big things that I've learned from doing this for a lot of years is it can be very helpful in revealing unintended consequences of implementing a particular approach. Sometimes solving one problem can create other problems, and so we have a little bit of discussion on that in an upcoming slide. But the bottom line is, kind of taken as a whole, these tools are really helpful in providing useful insights that can help us better account for and manage that uncertainty. So with this slide, I just want to give you a sense of what does it look like for the local modeling. So we're calling this the Potter Valley Integrated Flow Model, or PVIFM. And as Armin mentioned earlier, the similar graphic here, this red is the Potter Valley groundwater basin, and in black here is the Potter Valley Integrated Flow Model boundary, and it cuts through here. We basically chose to have an area. There's a really handy long record of stream flow information at a USGS gauge right here. So we've essentially taken the entire watershed that's tributary to that point, which encompasses the basin and the valley. It's about 94 square miles. And what we're doing is simulating monthly flow conditions over this 12-year period, October 2012 through September 2022. This particular model is three-dimensional, and it's subdivided into over 73,000 cells. Each one is spaced 100 meter by 100 meter dimensions. And then vertically, it's split into 3 model layers that, depending on where you're located, can represent a combination of channel alluvium, younger and older sediments, or bedrock. So that's essentially our Rubik's Cube there. It's split up into 73,000 cells. And the processes that it simulates are listed here and are just shown graphically here. Precipitation, stream and canal flows, we've got our diversions and deliveries, the recharge from that precipitation, as well as from applied water. You've got your groundwater flow system, your runoff, ET. There's a domestic pumping that we are simulating at this point, some groundwater surface water interaction, and groundwater discharge to land surface. So with that, I'll turn it back over to Armin.
Thanks, Nate. And so we want to transition, and I appreciate we've kind of provided some of the background work, and then we'll move into how that those analyses were used to look forward into water management alternatives. So this section of the presentation is really focused on what are the water management alternatives that could be considered, and we evaluated as part of looking at how the Potter Valley water supply could be managed in the future. We looked at kind of 4 categories of water management alternatives. The first one was looking at surface storage. What was the potential, or what is the potential for storing some of that water that will be available during the run of the river, diversions in winter and early spring, and could that water be stored in surface storage either tributary storage, on-stream storage, or pond storage to be used in the summer irrigation period. We'll talk about the conjunctive use, which is essentially how could we use some of the groundwater, either the groundwater supplies by themselves or the groundwater supplies with recharge component from the surface water to augment the water supply during the summer. We looked at 3 different methods there that Nate will talk about. We looked at operational improvements, largely building off of work that was done in previous studies, looking at irrigation delivery system, efficiency efforts, and also recovery and pump back systems. So that water that runs through the valley flows into Lake Mendocino, and we looked at how that water could be used to be pumped back into the valley in summer irrigation. And then we also looked at demand management opportunities, so on-farm irrigation system improvements that might reduce the demand for water from Potter Valley Irrigation District. So we'll touch on each one of those 4 in the next slides here. So the first one we'll look at is surface storage alternatives. And again, 3 components. The first one that we'll look at, that's okay, we can go to the next slide. The surface storage investigation, really the key question was, what is the potential for surface storage with the decommissioning? And we built off of the 2021 McMillan study that evaluated some of these potential tributary locations. We pulled geospatial data and elevation data for all of the entire study area. And then we looked at potential tributary areas that might have the opportunity to create enough storage to manage this water seasonally. All the areas that we did investigate are all shown on the map to the right. You can see there's about a little more than half a dozen locations that we looked at. And each of those we looked at what would varying dam heights provide in terms of storage capability behind that dam. The Bush Creek, Boys Creek, and the unnamed creek near East Canal were evaluated in the 2021 McMillan study. We expanded that to look at Williams, Hahn Creek, White Creek, Burritt Creek, and Munevar Creek. And then we also did a preliminary evaluation of what a dam on East Fork Russian River might look like on the river itself, and that's the one labeled EFRR on the map. Each one of these areas in the map is showing what potential inundation might occur if you had what we called low, I believe is 100-foot dam height, medium was 150, and high was 200-foot dam for the tributary storages. On the East Fork Russian River, I believe it was 10, 50, or 20, 30, and 40-foot dam heights. The kind of cut to the chase on, well, actually the next slide I think gets us to that. Each one of those tributary locations were evaluated in terms of its storage potential. We also evaluated what would a dam height, how much dam height might be required, and what storage you get for it, what would be the length of a dam, how much storage capacity, and how much inundated area behind the dam might occur. We also looked at the distance to the powerhouse, because the water that's stored here would be provided back up to the head of the valley and distributed through the existing canal systems. And then we looked at the natural runoff, so how much potential natural runoff occurs in each of these tributary creeks. The top performers in terms of highest storage potential for dam height or dam investment were Bush Creek, Williams, Hahn Creek, and Munevar Creek. Those are the top 3. And you can see with Bush Creek, and Bush Creek in particular is a higher efficient watershed in terms of storage potential than the others. The Munevar Creek has quite good storage potential, but it's almost 7 miles of canal back to the pump to the head of the valley. Bush Creek is quite close. With a 100-foot dam, there's almost 5,000 acre-feet of storage potential created. With a 200-foot dam height, there's over 25,000 acre-feet of storage potential created. Each one of these required very high dam heights. So all of them were over 100 feet to provide storage potential that might start to create the capacity to store and distribute summer irrigation water. The Bush Creek Bush Creek location in particular was the highest performing, and we've got some evaluation of that in the next slides. We also looked at in-valley pond storage. There are a number of ponds, I think roughly 120 acres of ponds within the valley as of 2023. I know there's new ponds that have been developed in the last year or so. These are primarily been used for frost protection and water storage, as well as some domestic uses. So we wanted to evaluate what would it look like if you magnified and amplified building of those ponds throughout the valley. We looked at roughly the ponds currently provide about a little under 700 acre feet of total storage. And we wanted to look at, well, what if you really expanded that? So we looked at trying to create the potential of maybe 5,000 acre feet of storage. We assumed these dams would be kind of 10-foot berms and filled to about 8 feet. And then we wanted to evaluate just how the locations that we focused on were areas that are either currently fallow or idle or hay or pasture that might be more amenable to pond locations than others. If you can click the next animation. Okay, so just for evaluation purposes, we looked at the areas on the map that are shown on the right. They're numbered 1 through 6. And they were selected as regions that have high levels of either fallowing, idle, or hay or pasture. We're not proposing that these are the locations for ponds, but in order to do the evaluation, we had to select specific locations. And each one of those groupings, 1 through 6, are shown in the table in the bottom left, where we can see the total amount of acreage that might be developed through ponds in those areas and the storage capacity. And certainly you wouldn't develop ponds in these areas throughout, but I think the demonstration here is that there is sufficient capability to build storage ponds up to 5,000 acre feet. The total of all 6 of these was close to 8,000 acre feet. So there does appear to be a strong potential for strategic development of ponds throughout the valley, either in a distributed or in a focused area, to generate storage capacity. Okay, we have a summary of the storage investigations here. We have each one of these rows shows Bush, Williams, Munevar Creek, or the 4th row here is the East Fork Russian River Dam, where we looked at 20 to 40-foot dam heights. There are significant challenges with all of these, and the last row is the in-valley pond storage. All of the tributary storages are going to have high costs associated with high level of dam heights. When we get into the East Fork Russian River, the dam height is not so much the challenge, but in order to create storage, you'd likely be inundating both the roads that enter the valley there, and there'd be substantial challenges with moving of the roadways associated with that, which will either translate into a cost element or other environmental implications. The in-valley pond storage we looked at as well, that I just mentioned, and we've targeted up to 5,000 acre feet. This has the potential for being either a distributor or a focused implementation. Next slide. Okay, I think I'll hand it back to you, Nate, to look at the conjunctive use alternatives.
Okay, yeah, so we'll be talking about three approaches: supplemental groundwater pumping, managed aquifer recharge, and aquifer storage and recovery. So we started with three basic questions listed here. First off, how might the aquifer beneath the valley respond to no Potter Valley project? This is not a proposed solution by any means, but from a modeling perspective, it's always good to start with just physically, how might this basin respond when we just don't have those imports as consistently coming through the valley? So we started with that. How much groundwater supply could potentially be produced to replace some of the lost supply? So we've got some simulations geared around that. And then would application of managed aquifer recharge or aquifer storage and recovery be beneficial in the valley under no PVP conditions? So we built these sets of simulations around answering these questions. We established a baseline, which basically is just that same 12-year historical period, October 2010 through 2022. We included that because it was a period that we had good information on PVID deliveries. So that basically establishes that baseline simulation. Next, we take the baseline simulation, but then turn off essentially those inflows at the head here for the Potter Valley project. So the idea being, we look to the past where we had a set period of deliveries. We pretend that we repeat that past, but the Potter Valley project is not there for us. Next, we looked at supplemental groundwater pumping, where we take that no PVP simulation and add a lot of wells within the valley to see what the basin can yield. And finally, this MAR ASR simulation, where we took the no PVP simulation along with some run of river assumptions and looked at potential MAR ASR operation. So one thing I want to start off with here is, just thinking about baseline and no PVP. So this is that 12-year period. This is a water level hydrograph. And it's important to know this is the basin average. This is out of the model, that red area that we had shown you previously. If you take all of those model cells within the basin and then just average them each output month and plot them up through time, what does it look like? So these are depth of waters with 0 at the top, increasing with depth. And I've got this thicker line at 10 feet, just kind of as a visual reference. Green line is baseline. Blue line is no Potter Valley project. So as expected, during the ag season in those summer months, when you don't have the Potter Valley project, on average across the basin, it's a few feet lower than during the baseline. So that you kind of see the lows are lower. Interestingly, though, when you look at the rebound during the spring, the water levels are pretty similar during most years. The exceptions would be during some of these, extra dry years, they don't quite rebound to the same level, but, within 1 to 2 feet, again, across the valley as an average. So this, right off the bat, this simulation provides some insights, and it suggests that there's enough rainfall in typical years in the watershed to help the valley groundwater levels respond each spring. So that's an important finding from this modeling exercise. So the second question, how much groundwater supply could potentially be produced in the valley to replace some of the lost supply? So I'm showing here on this map on the right-hand side, 124 irrigation wells. Again, this red outline is the basin boundary. These areas in deeper brown, those are areas with higher transmissivity, and that just means based on this initial set of modeling where you see deeper browns, we're inferring those areas may have greater potential for groundwater production as opposed to the lighter yellow where the less productivity. So I want to stress that all these dots that you're seeing, this is not a proposed well field. So this is very conceptual at this point, just to get some initial estimates of how much might this aquifer yield if there are lots of irrigation wells distributed throughout the valley. So what we've done here is basically just put a well every, quarter to a third of a mile across the valley. And we limited depths to no more than 100 feet deep. So we're basically looking at keeping the wells above the bedrock. So if there was at least 100 feet available, we included all 100 feet. If there was less than 100 feet available, we just went as deep as we could without going into bedrock. The groundwater pumping was simulated just during the June through September months of each of those 12 years. So that's 122 days each year with no Potter Valley project. And so the answer to this question is the model would suggest you get around 3,500 acre feet per year, which is about a third of the average PVID deliveries during that 12-year period. So that gives you a sense of the answer to that question. The simulated well yields, I'm going to bring in some numbers here where you see these posted values on these points. Those are the average June through September pumping rates in gallons per minute over that 12-year period. And they basically range anywhere from 0. You can kind of see some zeros along this fringe here where the alluvium gets very thin. The wells don't make a whole lot of water, up to as much as 264 gallons per minute. And if you take all these numbers and average them, you get about 53 gallons per minute. So is 53 gallons per minute a reasonable average pumping rate for this valley? One place we look to is, DWR Bulletin 118, which indicates typical well yields are in that 50 to 75 gallon per minute with a max of 100. So just for comparison, if you take 50 to 75 gallons per minute times 124 wells that operate 122 days a year, the math on that would say that you're around 3,000 to 5,000 acre feet per year. And we're certainly, within that range. So that's one thing to consider. But the fact is, uncertainty remains regarding the actual aquifer properties here. We've taken a swing at it based on some initial modeling, but the reality is there's not a lot of wells in this valley that were available to hydraulically test. So there's uncertainty on those properties. There's also uncertainty on groundwater quality. You may have some areas that have enough productivity, enough quantity of water, but that the groundwater quality may not be quite what it needs to be for certain crops. And there's also uncertainty on what I'm calling a built for purpose ag well, what that might yield across the basin. I suspect most of these reported wells are just domestic wells, which tend to be put in with, cheaper drilling methods, not as shallow, smaller diameter. So, I mean, if you went in with the mindset of wanting to put in a highly productive irrigation well, ag well, you would use, more of rotary methods. You'd go deeper, have longer screens, larger diameters, spend more time on well development, and really do everything you can to maximize the yield out of that well. So there's uncertainty regarding that as well. So here's that same plot that I showed before, but now I've just added this gold line for the simulation that has the wells operating. And as expected, during the ag season, it brings water levels even lower than with no PVP because we're now removing 3,500 acre feet per year of water. But again, interestingly, are the spring highs end up being still similar during most years. Again, during droughts, during those couple of years of extra dry conditions, doesn't quite get up as high. But there's some hope here that there's enough rainfall in the basin that your spring levels could be similar even under a local groundwater pumping alternative. Before I leave that, I want to stress again, this is the basin average. So that means depending on your location, your proximity to an ag well, that means there's going to be some locations that have a lot more lowering than this, and there's going to be some areas that have less lowering than this. So the purpose of this slide is to give you a visual, just a sense of that. So what we're looking at is a groundwater level lowering under September 2020 conditions from this simulations where we've taken the difference between our baseline simulation and this pumping simulation as a color flood map. So this is the change in water table elevation. The more intense this reddish color, the greater the change. This is a 40-foot lowering, for example. So the basin average is about 4. You can see it's kind of in this orange zone. Most of the basin is kind of in that orange. But again, as you approach one of those 124 points, they can be as high as 40 feet. So when I spoke earlier about, unintended consequences, you look to develop 3,500 acre feet of supply, but there is a balance there, a consequence to consider with regard to existing domestic wells and how much could they tolerate from a seasonal groundwater level lowering. So uncertainty remains, certainly regarding these drawdown estimates that would actually exist across the valley from the operation of those ag wells. But this does provide at least an initial sense of that, which can help inform the thinking during the planning process. Lastly, here would application of managed aquifer recharge or aquifer storage and recovery be beneficial in the valley under no PVP conditions? So the way we approach this for MAR, we looked at 2 different approaches. First, during those winter months, we looked at releasing those run-of-river flows into Bush Creek here to see if there could be a good enhancement of stream bed recharge after groundwater pumping. So this is basically always paired with this same 124 wells pumping during the ag season to create some additional storage space so that when the winter flows come around, the idea is, can that enhance some recharge in here? The other thing is, instead of delivering to Bush Creek, we looked at what if those flows were delivered to flood pastures. So the pastures are shown in green. And so basically, during the winter months, what if you just land applied that water to these pasture areas? So that was looked at from an ASR perspective. Taking that same run-of-river water, what if you instead now inject directly into the aquifer? So what we did here was at these 21 locations, we injected that water into the subsurface to see what benefits that would have. Unfortunately, in all these cases that we looked at, these different permutations, MAR and ASR would not likely be beneficial in the valley because the basin mostly fills each spring, as I showed in those previous slides, just from natural processes. So in other words, these approaches work when you have storage to put it. When the basin's full, when the water's available, there's not a lot of opportunity for enhancing that. So last slide here, some things to consider. As Armin mentioned, there's some new wells that were put in recently. It'd be good to incorporate estimates of the aquifer properties from the well development at those new wells. I think it'd be also a good consideration to develop and implement an aquifer testing program that could include, say, up to a dozen or so wells. I've got red stars over here just as a visual. There's nothing particular about these points, but some kind of distribution of points here to put in larger diameter wells and actually test them to confirm or at least help us refine these estimates of productivity. And so that'll give us a sense of yields, and it'll also give us a better sense of how that might affect domestic wells and give us access to collect samples to see what the water quality looks like. And then basically just, it'd be good to update the Potter Valley integrated flow model as knowledge of this aquifer system evolves so it can continue to provide good decision support. And with that, I will turn it back to Armin.
Yeah, thanks, Nate. So wanted to round out the alternatives with the last 2 groupings, which are operational improvements and demand management alternatives. We looked at 3 elements of those. One was irrigation delivery system. So really, how could the canals and the delivery system be improved in terms of reducing losses and managing flows more efficiently? The second component was looking at on-farm system irrigation efficiency improvements, and then a pump back system. And we'll talk about each of those on the next slide. The first 2, we're looking at either the delivery system or the on-farm irrigation demand management. This map on the right is essentially the layout of the canal system and the delivery locations for Potter Valley Irrigation District. There was previous work that looked at irrigation delivery system improvements that could modernize the canal operations. We know that a number of the open canals have been converted to closed pipes in some areas of high seepage, but that could be expanded much more broadly throughout the irrigation delivery system. Looking at water level control, flow management, and integrating that with a SCADA system to basically automate and optimize control. That has been estimated that could reduce system demand by 20 to 25% if those investments were made on the irrigation delivery system. Then looking at kind of on the on-farm side, we looked at kind of the evaluation of tailwater recovery, irrigation system improvements, crop management. And while these ranges could be quite high, we felt like a reasonable range of demand reductions could be somewhere in the order of 1 to 3,000 acre feet through some of these efficiency measures, through some deficit irrigation aspects to the cropping and the irrigation management. The last one we looked at and largely built off of work done by the Macmillan report in 2021 was a pump back system. So in this case, it was looking at that winter water that might come over from the Eel River. Any water that couldn't be used in the valley would flow down the East Fork Russian River, flow into Lake Mendocino. And this concept is to look at, well, if that water is stored in Lake Mendocino, could you install an intake at Lake Mendocino and build a canal and pipe through that, or build a pipeline and pump through that pipeline to deliver water to the head of Potter Valley. That concept includes about 13 miles of canal, a pump station at Lake Mendocino, and it was sized in the previous work at about 10,000 acre feet. It could be optimized to be a little bit lower than that based on our assessment, but we took their work kind of verbatim. There is a challenge of the water that is not used within the valley, and once it hits Lake Mendocino, becomes a more challenging ownership and water rights issue. That water is generally considered water rights to the Russian River users throughout. So this one both has a technical challenge, a cost challenge, and also a water rights challenge. Okay, so next, so I want to bring it all together now. All the water management alternatives, we have run through a process that looks at both the cost of those as well as other evaluation criteria. And from the cost assumptions, we took all of those alternatives and developed capital and annual O&M cost, operations and maintenance costs associated with them. The types of analysis that we've conducted really are what we call class 5 level cost estimates. They're determined. Class 5 is a kind of a standard protocol for cost estimating that gives a range of -50 to +100% on the capital cost. My experience has been almost all the costs that we do are far better than that range, but that is the range we should consider, given that they're conceptual level estimates right now and not based on specific engineering design and land ownership aspects. All of the capital costs were annualized into present value using kind of a 30-year term and a 4% discount rate. And then we looked at other evaluation criteria as well. We know cost is important, but it's not the only evaluation criteria. We looked at obviously yield and cost as kind of the drivers of, does it make sense? Is it feasible? But we also looked at timing of implementation. How long would it take for a project to be implemented? What are the reliability, flexibility challenges, environmental challenges? Does it have a high energy use? Does it have a really challenging permitting legal aspect? What jurisdiction? Could Potter Valley Irrigation District do it by themselves, implement the project by themselves, or does it require many partners? And then lastly, we brought in kind of a phasing potential. Does it have the potential to be phased over time? Okay, so on the cost evaluations, this is a summary of the cost estimates associated with the alternatives that we did evaluate. The way this table is structured, we have each one of the alternatives is the columns in this table. Each one of the rows is listed there. We have first row is the average yield in acre feet per year. We have the type of alternative where we wanted to identify whether the alternative could be implemented as a standalone solution for the water management challenges, or could it be a component of a larger solution? We have the capital cost and then the annual O&M costs. The first two columns here are the irrigation delivery system and on-farm management, and you can see we're upwards of 3,000 acre feet of potential demand reductions savings associated with both the irrigation delivery system and the on-farm. We're still developing the cost for the on-farm management, but the irrigation delivery system are somewhere in the order of $8 to $10 million for implementation. The next two columns, the next three columns are in Valley Ponds, tributary storage, and the Russian River, East Fork Russian River Dam are the surface storage elements. You can see the potential yield. Each one of those are potentially providing up to 8,000 acre feet of yield of storage and creation of summer water. The tributary and the East Fork Russian River dam storage elements are upwards of $200 million of capital costs associated with them. They're quite complex in their implementation. We've estimated somewhere between 125 to 250 for the tributary storage. The in-valley ponds are substantially lower cost investment, roughly 15 million to 28 million to generate somewhere on the order of that 5,000 acre feet of total storage potential. The groundwater supply options that Nate discussed, we looked at a range of roughly 3,500 to 5,000 acre feet, and with a capital cost of somewhere between 19 and 22 million dollars for developing of a well field, and then somewhere between 0.3 to 0.8 million in annual operating costs. And then the last column to the right is the Lake Mendocino pumpback system that was estimated at 10,000 acre feet of potential water that could be pumped back, over about $100 million of capital costs invested. All of these costs, I just want to be clear here, they do not include the costs associated with the proposed new eel Russian facility. These are costs associated with developing these individual Potter Valley water management alternatives, not the eel facility. Okay, next slide. Okay, so like I mentioned, we looked at criteria other than costs as well. So we tried to bring it all together in this table here and there. So we have yield, cost, timing, flexibility, environmental impacts, permitting, jurisdictional complexity, and phasing potential. And in each one of these, we have ratings where we essentially said, is it a low rating associated with that criteria, or is it a high rating? So L is low and H is high, M is medium or moderate. And really what we're trying to identify here is the greens, which are kind of the best performing across each of those. You can see that we've got lots of high yielding, but really high costs, big timing aspects associated with the storage facilities. Now we've got mixed ratings associated with a number of the others. You can see the in-valley ponds and the groundwater supply are both have kind of moderate supply potential, but are fairly good on the other evaluation criteria. So our report will demonstrate the values of each one of these and document the basis for them. But essentially, this table can be viewed as kind of green being positive for that criteria, red being less positive for that criteria, and using this to help inform how you might package together a portfolio of actions to move forward with. The next slide. Okay, and I think this is the last of the analytical slides here, but we're hoping this graphic is helpful in thinking through water management alternatives. What we've done here is the x-axis represents any new storage that might be developed, either tributary storage, pond storage. And then the y-axis represents any new supplemental supply that might be developed or needed. And then each one of the lines that goes across diagonally across the graph here is representing a line of demand reduction, essentially efficiency improvements that could be implemented. So if you hit the first animation, thanks, Nate. So just looking as of today, if there were no new investments in storage, no new investments in additional supply, there would be a need for about 8,000 to 9,000 acre feet of additional supply needed to meet that irrigation season demand if there were also no changes in efficiency improvements. Alternatively, if we hit the next animation, you could invest in this one. This point is showing if you invested in about 20% demand reduction through irrigation system improvements or on farm, and you invested about 2,500 to develop a roughly 2,500 acre feet of new storage, then you might need somewhere on the order of about 5,000 acre feet of additional supply, looking to the x-axis. And then all the way to the far right, the next animation looks at a case where you made larger investments in efficiency, so you were able to reduce your demand by 30% through efficiency improvements. You built up to 5,000 acre feet of new storage, and that largely closes the gap. Maybe there's about 1,000 acre feet of additional supply that is needed. So we developed this graph and kind of trying to shape the scale of the problem and think about the combination of both efficiency improvements, which are the lines in this graph, investments in new storage, which is the x-axis, and investments in new supplemental supply, which is the y-axis. And we think each one of those alternatives and combinations of alternatives essentially falls on this graphic here. Okay, I think we'll go to the next slide, which is our wrap-up slide. So our current, where we are in the process right now, we're preparing our final simulations with the water management alternatives. We're refining our cost estimates. What I showed here previously are draft. And then we're completing the evaluation process for each of the alternatives. We hope to have a study report that is for the management team's review in January, and then that should be made publicly available through both Potter Valley Irrigation District and Sonoma Water in early 2025. We have some recommendations for the next phase. We think we have found some unique and interesting combinations of alternatives. We think there needs to be further refinement and field verification of the promising alternatives, in particular groundwater production for a large-scale water supply. And then we need to move these from conceptual to feasibility level. And the cost estimates will be updated and refined as part of that as well. Those are our recommendations for the next phase of work. Okay, and with that, I think I'll hand it off to Janet to close us out. Thank you very much.
Thanks, Armin. A lot of information. And I think it's your graphics and everything are very clear. If people have questions about this, there are several different contacts that you can have to use. For me, pottervalleywater.org or Mendocino County IWPC.com. And those are websites that you'll also be able to find more information going forward. Stephen Maples with Sonoma County Water, his information is here, and Armin with Jacobs. And in summary, I'd like to just take a minute to thank Potter Valley Irrigation District Superintendent Steve Elliott for his help coordinating meetings between the Jacobs team and farmers in Potter Valley to gather this information. Steve also provided Jacobs with a lot of data about the crops grown in the valley, water used during the irrigation system, and amounts of water that are diverted, as well as how the irrigation district system is operated. Special thanks to landowners here in the valley who helped by allowing monitoring of existing wells, and also some of them who actually allowed new wells to be placed on their properties. So very important for us for gathering data into the future. And finally, I want to thank Sonoma Water for their help with attaining the grant funding, and to Armin and his team at Jacobs for all of the on-the-ground work in Potter Valley, the analysis of their data, and a description of next steps. There are many more questions to be answered, and there's a lot of work that needs to be done. And I'm hoping that the results of the next investigations we'll be able to present to the public in another forum in the near future. Please take advantage of these websites for more information and contact us with questions. Thank you very much for your interest and look forward to bringing more information to you as soon as we can.
Great, thank you. We are now